So this was what a Lie group is for us. It's basically a group in which every element has coordinates. We take a small enough neighborhood or some neighborhood of the identity. Typically, the identity belongs to this neighborhood. That's the one we are focusing on to begin with. You have a map phi which maps every element there to a bunch of R real numbers. So phi of A, for example, would be my bunch of parameters alpha 1 to alpha R. Phi of B would be beta 1 to beta R, and so on. And we also said that since basically the major thing that you can do in a group, in fact, the only thing you can do if you have a group is multiply elements, you should be able to tell me, given the fact that the parameters uniquely tell you what the element is. So if I know this, I know A, which is phi inverse of the alphas, and you compose it with phi inverse of the betas, the resulting element is, of course, okay, what is this? Is this C or the coordinates of C? This thing? What is this? Phi inverse alpha is, of course, nothing but A, right? Phi inverse beta is nothing but B. So when you compose them, you get C. If you apply phi on this map, what you get are the coordinates of C, that is, things we have been calling gamma. So what we have at the end of the day is the coordinates of the composite C can be written down in terms of this rather complicated looking object, but which ultimately is nothing but some function f of alpha, these parameters, and beta, these parameters. So this is our central object. If you know what this function f is, you essentially know everything about a Lie group. And we had also said that this object has to have some properties which it automatically inherits from the fact that G is a group. For example, 0 being the, so this is basically always conventionally chosen that the identity has parameters of 0, in which case pi 0 semicolon alpha or f alpha semicolon 0 will all be alpha. You're going to definitely get back the same parameters that you started with. And as I said, this means that if I expand f alpha semicolon beta in powers of alpha and beta, then for fj, you can only have this kind of form. At the second order in alpha and beta, this clearly tells you that this is the only kind of form you have. Even at higher orders, then only have mixed terms with both alpha and beta. You cannot have terms which are pure alphas or pure betas. So this is something which follows simply from the fact that the identity exists in the group and is parameterized by a bunch of zeros. Now, we also said that we would like to take a look at what happens to elements which are close to the identity, in the sense that it's an element which has parameters which are close to 0, especially what happens when you compose such an element, let's say delta alpha with alpha. And there, simply, this is going to follow. So this is what we have already talked about the other day. This is basically Taylor series, nothing but that. And this is, of course, alpha j. And these quantities are going to turn out to be very important. These are what we call the eta jk's. And of course, these are simpler than the f's because they depend only on alpha and not on beta. But as we are going to argue that if you know the etas, then we should be able to reconstruct back the f's. So the etas, which are simpler, have all the information that you need in a sense. And we also argued that since eta jk 0 has to be delta jk, after all, if this is the derivative you are calculating, if you're calculating the derivative where alpha is 0, then you're actually differentiating beta j with respect to beta k, right? So at alpha equal to 0, this can definitely be inverted. The matrix H of alpha, which is the matrix, okay, there's not H, there's capital eta, but frankly, we would often call it capital H just because that's what Latin taught us for a long time. We would expect that at alpha equal to 0, this being invertible, this being simply the identity, and hence invertible implies that there is a neighborhood around the identity where this matrix can be inverted. And therefore, we also introduce the inverse matrix xi of alpha, which is nothing but H alpha inverse. So this was our xi. And in terms of components, it meant I think what I will need to do is, okay, there are too many things running right now. Maybe that slowing my system down a bit. So this was what we had done in the last class. Any questions about this before we proceed to today's class? If not, let's go on. So today, as we said, we will need to exploit other properties of F, in particular, properties which follow from the associativity, and see how we can use the etas and the xi's to build up F, and what consequence that has on the structure of it. So associativity, of course, has this basic claim that if, since C of AB is CAB, this immediately follows. This is something we also did at the end of the last class. Well, actually, these should all be semicolons, but I might forget to put semicolons and just write commas. It's too much of a bother to put a dot on top of every one of the commas. Now, of course, remember when I write this, I mean F as a whole, but of course, this is valid also for the components. So here, in order to proceed, what we will do is we will first differentiate both sides of this equation. I will write the equation for the jth component and differentiate that with respect to gamma k. Okay, let's see what happens if I do that. We have to be a bit careful, but all we are really doing is using standard rules for partial differentiation. So what happens when you do it on the left? It's simple. You get del fj, del gamma k. The fg, of course, has these as arguments. What happens when you do it on the right? There you have to be a bit careful because the right also depends on gamma, but it depends on gamma through the f gamma a here, gamma alpha here, right? So let's call this delta, just to make notation nicer or a bit simpler. So when you do this, what you do is del fj. Of course, you have to do that, but you can only differentiate fj with respect to delta. You can't differentiate that directly with respect to gamma, right? Because it depends on delta and beta. So del delta L. Of course, delta here is my shorthand for F gamma semicolon alpha. Okay, times obviously del of delta L. Delta L, of course, is FL gamma semicolon alpha. Is this clear to everybody? This particular step. There's nothing but the chain rule for partial differentiation used properly. Is it okay?
So here L is summed over, right?
Yeah, this is summation convention, of course.
Okay, okay.
So there's sum over all L. I'm going to assume the summation convention is valid unless I otherwise state. Okay. In fact, we used the summation convention a while ago, right? I don't know what's happening to my previous pages. Somehow I'm losing them all the time. But anyway, when I wrote delta Fj is alpha j plus eta jk delta alpha k, then of course was a summation over k. This is also a summation over L. Right. Now, let me remind you that del Fj del beta k or beta semicolon alpha at beta equal to 0. What was that? What is this quantity called?
Delta.
No, this is eta jk, right? This is what our definition of eta jk is.
Yeah, yeah, yes.
When you put alpha equal to 0, you're going to get delta jk here, but this is what eta jk is. Now, let's use this definition in this equation. To do that, I will put gamma equal to 0. If I do that, what happens to the thing here? If I put gamma equal to 0,
With eta jk f of alpha beta.
yeah, it becomes eta jk, but eta jk at f of alpha semicolon beta. Good. What happens to this one? Let's look at this first. When you put gamma equal to 0, this simply becomes, there's nothing but this, right? When you put gamma equal to 0 in this derivative, you actually get just this. Is that clear?
Sir, so we put delta is equal to 0, right?
No, we are putting
Sorry, gamma is equal to 0.
gamma equal to 0.
So then it should be f of alpha semicolon beta, right?
Which one?
This expression in the argument.
That's what I wrote, didn't I?
No, like not f of alpha semicolon beta, but rather f of alpha semicolon beta.
Didn't I write that? That's what I can see on my screen. Eta jk of f of alpha semicolon beta. That's what you're saying, right?
Okay.
Oh, I'm a bit confused. That is what I did write, right? Are you seeing something else?
Sir, I think he's saying that the alpha should be an argument of f and semicolon beta should be outside.
No, that can't be. First of all, f has to have two arguments. Remember. And we're putting gamma equal to 0 here, right? Now, the point is, when you do this, del fj del beta k beta semicolon alpha at beta equal to 0, eta jk becomes a function of the other argument. Here, you're putting gamma equal to 0 after differentiating with respect to gamma k. Remember, gamma is the first argument. You're differentiating with respect to first argument, and then putting the first argument equal to 0. It will be eta jk, just the same as this, with the second argument in its place. So the second argument is f of alpha semicolon beta. Is that clear? Just notice that here, the second argument is what becomes the argument of eta jk. And the first argument is what you're differentiating against. Does it make sense now?
Yes. Yes. Thank you.
Okay, what about this one? Again, you are differentiating the first argument and then putting the first argument equal to 0, right? Of course, when I say you're differentiating with respect to the first argument, I'm oversimplifying. You're differentiating with respect to the kth component of the first argument, and then you're putting all the components of the first argument to 0. But that's again eta jk, right? Or eta lk in this case. And the second argument is here. But what happens to this when you put gamma equal to 0? No, then gamma is not the argument you're differentiating in respect to. So here you don't get an eta. But when you put gamma equal to 0, what happens to this delta?
Delta becomes alpha.
Right? So basically, the first piece here simply becomes del fj Does that make sense? The delta simply becomes alpha. Is it okay? This is what happens when you put gamma equal to 0 after doing the differentiation. Okay, but notice that this actually gives us a rather interesting result. What exactly are the eta jk's? They tell you how the function changes with the first argument when the first argument is at 0, right? That's what eta jk's do. Now, in this equation, you have eta jk on the left, evaluated at f, eta lk on the right, evaluated at alpha. And these are all rates at which the function will change, f will change, with the kth first component, but only at alpha equal to, at the argument equal to 0. But what about this? This tells you how fj will change with respect to the first argument, the nth component of it, but at any value of alpha, right? I'm not putting alpha equal to 0 here at all. So the important thing here, and this is what the group structure actually forces on you, is that the rate at which this function depicting group composition changes at any value of its parameter is actually controlled by how it changes close to the origin. In other words, what happens close to the origin dictates everything, essentially. Is that point clear? This is the central point, actually. Things that happen close to the origin controls the entire group behavior. Which is why, when we study Lie groups, very often we just look at Lie algebras, which in the language of differential geometry is nothing but the tangent plane to the manifold at the origin. Basically, you're looking at things which happen very close to the origin, and that's going to tell you almost everything about the group. Apart from some global topological properties, everything else about the group is there in the eta jk's, or is there in what happens close to the origin. Well, actually, let me just point out that I can rewrite this equation to give an equation for del fj del alpha. Okay, and let me do this a bit carefully so that we will actually have to use this argument in a much more complicated situation soon. So let's do this a bit carefully so that we can handle the more complicated case later. Notice that here on the left hand side, which ones are the free indices, which ones are the dummy indices, you have to check first. Which ones are the free indices on the left? On the left, of course, left is this.
J and K.
J and K. And there are no dummy indices on the left. But on the right, of course, J and K have to stay free indices if this equation is to make sense. And L is a dummy index, right? So L being a dummy index, you can't do much with that. But if I want to actually solve for this, I need to get rid of the eta. How would I get rid of the eta? How can I get rid of the eta from the right hand side?
Multiply by xi.
Oh, well, actually contract with xi.
Contraction.
Multiply by xi, of course, will not really work. But you have to contract with xi. Sum up over some indices so that you can introduce a delta. Okay, let's see. Let's rewrite this eta jk f. Now f, I'm not writing f of alpha semicolon beta because I know here alpha and beta are the only things that you have. So you'll have. But this one, I want to write alpha semicolon beta here simply to emphasize that here, this is the derivative you're doing. This is what I already had, but now what I will do is put in a xi on both sides. I have to contract, but contraction can only work with free indices, something which is already a dummy. You cannot contract on that. Right? That is one mistake which people make all the time in calculating things like this. Forget which ones are the free indices which are available for contraction. Let's say L prime. Of course, if I do this, the same thing on the other side as well. Right? But when you do this, what does this become? What is
Delta
this?
L L prime.
And there's a sum over L, which means that this thing becomes delta L alpha L prime. Everything else goes away. So you get finally the most important equation for today. Or, well, second most perhaps, if I can get to the most important equation today. I'm not very sure whether I can get that far. Let's see.
Sir,
Yeah.
right hand side you multiplied with epsilon on the right, but on the left hand side you multiplied by the
These are
left
numbers,
side.
right? You're right. If this had been objects with operators or matrices, I would have to be careful about the order. But these are numbers, aren't they? The functions are real valued functions. You're taking their derivatives at a point. So that's the value of eta jk, right? Which is a number.
Oh, yeah, they're numbers.
So it doesn't really matter. But since you have raised this, let me do it the way you want it. Of course, this equation gave me L prime on both sides, but I can always change that back to L. Okay? Right? Now, why is this equation so important? This equation is extremely important for one very simple reason. What does this tell you? What if I know the etas, then I also know the xis, right? And all the etas, the xis will automatically follow from inverting the matrix of etas and looking at the components. So if I know etas and xis as functions, I know the right hand side, which essentially means this becomes, well, I don't really know the right hand side because the f is stuck as the argument of eta. But what does this become? This becomes a bunch of coupled first order PDEs, partial differential equations, for the functions f1 to fr. So the moment you know eta xi, you can write down these equations. Okay, these are telling you how f changes with alpha. The first argument, right? But the differential equation alone cannot help. You need the initial condition, but that's also easy. How much is this?
Beta.
Beta j. So if you give me this set, what do I have? I have a bunch of coupled partial differential equations, first order each in alpha, which tell you how f is going to evolve with alpha. So if you start with a particular bunch of betas, you should be able to find out what the function is. So betas just serve as parameters here. And once you choose a bunch of parameters beta, I can find out the full f of alpha beta by solving this equation. Start from f of 0 comma beta, solve the partial differential equations, and you end up with f of 0 comma beta, f of alpha comma beta, the composition rule. Okay? So if you know the etas, you essentially know the composition rule. This is a bit of a, well, facetious statement, simply because if you think about it a bit, the f is stuck here on two sides. One is the partial derivative on the left. That's straightforward. Del f j del alpha k, alpha l. On the right hand side, you have eta jk of f. And depending on eta jk is some function of its argument. So depending on eta jk, this might be a horribly nonlinear differential equation, right? So it may be very difficult to solve this equation. I'm not claiming it's going to be easy. All I'm saying is, in principle at least, whenever you have eta, you can find the size from there, and you can construct this equation, and this gives you a complete way of finding f of alpha semicolon beta for every bunch of betas that you can think about. Whether it's easy or difficult to do, we are not going into that, but in principle, it's done. Clear?
We need the betas as well to find out the whole
So
solution.
you don't need, look, you don't need the betas to find, betas are alphas and betas are independent variables, right? You never need alphas or betas. You put in alphas and betas and ask what the output is going to be. So here you start, okay, suppose I want what happens when, say I have two parameters each, that is alpha and beta both have two components. So suppose I want to find out what happens when beta is, say, 0 and 1. Beta 1 is 0, beta 2 is 1. I just solve this bunch of partial differential equations. I want to know what happens when beta is 0.2 and 1.1. I solve it again. Actually, I don't really have to solve it again. Betas come in as parameters in these partial equations. So formula automatically handles betas. You change your betas, you get a different solution. That's it.
So these are like different initial conditions.
These are initial conditions for the partial differential equation.
Okay.
So in principle, the job is done. If you know the etas, you know f's. Now, there may be some questions raised here. One is, okay, we use associativity, right? We started with associativity, and from that you differentiated and ended up with this equation. But now, is it necessarily guaranteed that if I solve this equation, I will necessarily get a f which obeys associativity? The question is, the answer actually, okay, is non-trivial. Why? Because it might seem that since we started with associativity, did a differentiation ended up here, then that's all there is to do. You're done. But actually, things are not that simple. Actually, what happens is you may have to, in fact, you will have to check whether these functions that you get by solving these PDEs actually satisfy associativity or not. Okay? So that is a task that we have to do. But I'm not going to do that. You are in an assignment. It will show, you will show that actually this will satisfy associativity. But now comes a really important question, which is, if somebody gives me a bunch of etas, I say, okay, I've given you the etas, now go and find the group. That is, reconstruct the group from the etas. Can I do it? In other words, um, if somebody just pulls up a bunch of etas from thin air, then all you have to do in principle is this, right? We just wrote that down. Del Fj, del alpha k. Okay, I'm changing the dummy variable, the variables here, but that should be easy for you to follow. You know, what I'm going to do is, I'm not going to use L or something. I'm going to, for the rest of the class, which is, I'm going to do some rather nifty manipulations. So what I will do is I will keep track of which ones are dummies, which ones are not. To begin with, at this stage, J, K, L, etc. will be free indices, and PQR will be dummy indices. And to begin with, at least.
Sir, I had a question.
Yeah, go ahead.
In effect, what we did is, if f is associated, then it should follow be a solution to this differential equation, right?
Yeah,
That's what we proved. Like in general, any f cannot be associative.
well, of
Not
course, but
necessarily.
if it's an F which describes your group, it had better be associative. Because the group is, F is not associative, but F has a property, which is this one. Sorry, where did that go? Now I've lost my second page. Something strange is going on here. I'm losing. This property that we talked about is not really the property which you can say that F is associative. At least that's not the name for this property. This is a consequence of the fact that the group product is associative. This will lead to this. Okay.
So that's because of the group product.
Yeah, the group product being associative leads to this. And from that property, we ended up with this equation.
Okay.
Okay. The question could be that if I solve this equation, I said I'm claiming that there's a bunch of partial differential equations, which we should be able to solve and get f back. If I solve and get f back, will that necessarily satisfy? Okay, I hope that, yeah, hope this is. Will that necessarily satisfy this equation? And that means, will that necessarily ensure that the group product is associative, which it has to be in order to form a group? The answer is yes, but it's a non-trivial thing. You cannot just say, because I started with associativity, got here. I cannot claim that anything which satisfies this will also give me something which leads to associativity. You have to prove that. But I'm not going to prove that. I'm going to leave that as an exercise with hopefully enough hints in this next problem sheet, which will be up maybe tomorrow. Okay? Now, all seems very straightforward. Somebody gives me etas, I just plug this in this partial differential equation. If I can't solve it analytically, at least I can do it numerically. What's wrong with that? This is a bunch of coupled first order PDEs. You can always solve them. Or can I? Can you anybody spot that whether we can always solve a bunch of equations like this? You've done your numerical analysis course, you should be able to figure out how to do this on a computer, for example. But can you always do that? Or is there something that we need to worry about? Some condition, maybe. This is a first order partial derivative, right? When we talk of partial derivatives, isn't there a condition that immediately springs to mind? Not about first order partial derivatives, but about second order partial derivatives.
The
Come on.
commutativity.
Yeah, the fact is, if you do it in a different order, you should get the same answer. Okay. which actually becomes a huge condition on the etas. If somebody just gave me a bunch of etas and told me to solve this set of equations, I simply may not be able to, because that might be inconsistent with the basic principle property of partial derivatives. Just the same way, somebody gives you a force and says find the potential. All you have to do in principle is just solve dv equal to f minus f dot dr, right? But you may not be able to, because that v may not be an exact differential. It fails the first and foremost test of an exact differential. Similarly, if I want to solve this for an f, that means that df, which is del f del alpha k d alpha k, this quantity is an exact differential. But it may not turn out to be if I just choose any etas. That is, there has to be some conditions which we call actually integrability conditions. That is, that will allow us to integrate these differential equations. Okay, and those conditions will turn out to be very, very useful in the long run, because that will give us a first hint that, well, about a basic thing which comes in Lie algebras. Let's see why. Okay, so what do we have to do to check integrability? Any suggestions? I should start with this equation. Then what do I do? What I need to check is this, right? That this is holding. If this holds only, then there is a legitimate possibility that we will be able to solve and find our f's. You all agree? I'm hoping that means that there is no disagreement about that. Or is anybody? This is a very important point. So if you have a confusion, please speak up. If not, let's look at what this condition tells us. Let's differentiate this partially with respect to alpha L. Now, f here is always f of alpha semicolon beta, so I'll just write f. On the other side, what will we have? Xi p k comma L. Alpha. Done. But is that enough? Is that all?
Eta JPs are also implicit functions of alpha.
Eta JPs are also functions of alpha. Although they're functions of alpha implicitly, as you say, through the f. So that's why I left it to a next step. And I said I'm going to use PQRs for dummies. So I will differentiate this with respect to Q. Q meaning FQ of alpha semicolon beta. Okay, I'll just write F, as I said, because F is always a function of alpha semicolon beta times right? Once again, partial derivative, just chain rule for partial derivatives. I just differentiated the first term here with respect to alpha L and resorted to the chain rule to get to this. And the commas, of course, are partial derivatives with respect to the nth argument. Now, what can I rewrite this as? I want an equation entirely in terms of etas and xis. So this partial derivative, how do I rewrite this? How to partially differentiate f with respect to alpha is right here, right? So what is this quantity going to be? Okay, any questions about this? Does this make sense? Yes, does this question, does this thing make sense? Oops. Yes?
Yes, sir.
Okay, then somehow I think my board has died on me. Hold on. Yeah. So we are actually through with this guy. It's a pretty nasty looking calculation, but it's a matter of simple partial derivatives, nothing else. So some people will call this a very difficult calculation, but it's really not. It's length. Okay, I'm just rewriting one thing, which is I will just want for later purposes to make this Q. But how do I make this Q? Simply by rewriting the dummy names, right? Eta j p comma r of f, eta q j f, rjf, the qr, so I will just change it to rq. So two etas, one a derivative, one actual eta, two xi's, and here one eta, one xi derivative. Okay? That's what del 2 fj del alpha L del alpha k is. But what does it have to be equal to? It has to be equal to del 2 fj del alpha k del alpha L. But can anybody tell me what that is going to be without doing any calculation?
It should be eta jp epsilon p lk
Epsilon, there is no epsilon here.
in
Unless
what
my handwriting.
xi.
Xi. Yeah, it will be just what you have on the top line, except that all the L's and K's will be interchanged. That's it. These are exactly the same. Xi q k alpha, xi p l alpha. Okay. So these two things, this line and this line, have to be equal to each other. How do you ensure that they are equal to each other? Well, if they're equal, then the difference is zero, or I can take this one, for example, to this side and write eta jpf times xi p kl alpha minus xi p lk alpha equal something else. But before I do that, I will do one more thing. And you will soon see why I need to do that. Okay, when I take this to the other side, the eta jp is common, right? When I take this term to this side, if I take this to that side, this has to come to this side, right? The first two factors are common, right? So you will get just this minus this. But it will be easier for us if I have the xi's in common. That is, I have xi ql, xi pk on both sides. Can I get that? Xi ql, xi pk here. I already have that here. And I also have that here, xi ql, xi pk. That's actually very easy. All I have to do is sorry. You see what I've done? All I've done is use the fact that P and Q are dummy indices and have used that, sorry. Use the fact that P and Q are dummy indices to interchange P and Q in this expression so that the factor involving xi's here is the same as the factor involving xi's here. Clear? Any questions? So we are nearly done. Okay. This looks like a rather lengthy and messy thing, but it is. It's rather rewarding at the end, but let's see what happens. If I move this term to the other side, I get what else do I get? Equal to, on the other side, okay, let's write the other side in blue. Minus this thing, eta r cube. Of course, I don't really have to check that upper term again because all you do is p and interchange p and q.
Uh,
Yeah.
the
Go ahead.
partial derivative was respect with eta, right?
You're right. You're right. You're right. You're right. Perfect. These were wrong. On this side, you do have partial derivatives of xi on this side, but on this side you only have beta. Perfect. This is exactly what you have. But this is still not the end of the line because what I want to do is bring all the f's to one side. Note that these depend on f, like this bracket. These on the other hand depend on alpha. These depend on alpha, these depend on, this one depends on f. I want to bring all the alphas to one side, all the f's to the other. How do I get this eta jp f to the other side? That's easy. I use a xi, right? Is that okay? How do I move this eta jpf to the other side? Why? Because I want all the f's on one side, all the alphas on the other. So how do I do that? Once again, I have to remember, this is where what I said earlier becomes very important. You have to remember which ones are the free indices, which ones are the dummy indices. The dummy indices you cannot handle any further. The free indices can be contracted further and that is made into dummy. So which one is the dummy index here? A free index here in eta J pay F?
J.
J. Okay, about the other index, J has to go down here. Let's use ABC just to avoid any confusion. Here, just use A. Of course, I have to do it on both sides. If I do this, I've managed to get rid of the F from the left hand side. Right? This just becomes a delta AP, which is it just replaces the P up top by A. But I still have the xi's on the right. How do I get rid of them? How do I get rid of the xi's? How do I get
Contract
rid
with
of it?
eta.
Yeah, because xi's are of course inverses of eta and etas are inverses of xi's. So use etas on this side, two etas for the two xi's. And of course, once again, careful about the free and the dummy indices. And you have to do the same thing on both sides. So what does this equation ultimately become? The right hand side become the left hand side. Okay, first the left hand side. I've not written at alpha simply because I'm going to put it at the end. Right? That's what the right hand side becomes. Everything is evaluated at alpha. Okay? What about the left hand side? These two together give you delta QB. So all the Q's become B's, all the P's become C's. Right? Is that okay? Q's become B's and P's become C's. So what do you get? Equal to, on this side what you have is xi AJF. Okay, I'll not write at F because I'll just put that at the end. R okay, so what happens? Sorry. Or what happens here? Say all P's become C's. So eta are C and this becomes B over R. And then other term you don't even have to look at because it's just interchange of P and Q. This becomes interchange of B and C. Okay. So what I've done at the end of a lot of lengthy calculation is the following. I have written del 2f del alpha j del alpha k del alpha L and interchange K and L, equated the two, wrote down the equation that comes from there, brought all the alphas to one side, all the f's to the other. Now I'm going to make a rather important claim, which is about the nature of the two sides. What kind of an object? This side is a function. They were both functions of the parameters, right? This was evaluated alpha. This is evaluated f. So can anybody tell me what this is telling you about the value of these quantities? And that actually is the great result here.
They're each some constant.
Why?
Like one depends on F, it's on alpha. If we change alpha, then
Well, actually, it's easy to say, suppose I keep alpha fixed, but change beta. F, remember, depends on alpha and beta. Right? So if I keep alpha fixed, as you're rightly saying, if I keep alpha fixed and then change beta, this side will not change, but this side would have changed if this were a non-trivial function. The only way this can be an equality is that both sides have to be constants. This is exactly the same argument that you use in separation of variables. You get my point? When you do separation of variables for a partial differential equation, essentially argue the same thing. You split the equation in two pieces. One side depends only on x, the other side depends only on y. And then you say x and y are independent. You can change one without changing the other. So if these were non-trivial functions of x and x or y, then the equation could not be true. But because the equation has to be true, what you have found out is that both sides have to be exactly equal to a constant. Is there any confusion about that? So ultimately, this brings in a huge restriction on the xi's and etas. Both sides have to be equal to constants, and the constant, okay, not a single constant. How many constants should this be?
R.
R. No. How many free indices are on both sides? Which are the free indices? At this stage, K and L are dummy here.
ABC.
Yeah, A, B, C, all of them are free indices. Right? Here also A, B, C are free indices. Right? So this actually are R cube conditions. And R cube constants minus C. These are extremely important quantities called the structure constants of the group. We will see later that from the structure constants, you can essentially recreate them. So you don't even need the functions eta or xi. The functions eta were, of course, simpler than the f. And you might say, okay, I've got there, so it's nice. It's simpler things and in terms of which I can build up f. But our equation was telling us that. But now I'm claiming something even more striking. I'm saying I don't even need to know those functions. If you give me these constants, then I should be able to rewrite or recreate the group out of that. Once
So
again, go ahead.
what was R?
R was a dummy index.
You said R cube constants we have.
Sorry. I'm using PQR here as dummy indices, but I also earlier had another meaning for R. I'm sorry about that. The dimension or number of parameters which describe the group, the so-called order of the group, that we also called R. So please don't confuse that R with this R here, which is just a dummy index.
Is the order of the group and dimensionality the same, or they are different things? Right?
Not really. For the Lie group, there are essentially two different ways. The dimensionality of the manifold which the Lie group has is the order of the Lie group. That's a nomenclature. How many parameters do you need to describe a particular group element? Remember, we have been saying alpha 1, alpha 2, up to alpha r. This r. That's not this r. This r is unfortunately, I should have perhaps chosen not PQR but something else.
Okay, so the dimensionality of the
Manifold
chart,
underlying the group.
that is the order of the group.
That's the
Lie
order of the
groups.
group. Yeah. And we have been calling that R from the beginning. So because we have been calling that R from the beginning, I should have perhaps chosen some other set of, not perhaps, I should have chosen a different set of dummy indices here. But I hope that will not confuse you. This R is just a dummy index which runs from 1 to R. So that's actually bad petition. Maybe Alba. Anyway, it's a dummy, so it doesn't matter what you call it. Maybe I will call it M or N or something in a later version. Okay? Just not to confuse it with this. Now, note two things. First of all, this equation, this is equal to minus CABC is a bunch of conditions. As I said, R cube conditions. This R is the dimension or order of the group. Or order of the group in this case, for a Lie group, the order term is not used for the number of elements in the group. I guess that's where the confusion is coming from. The number of elements in a Lie group is typically infinite. Right? So order in that sense, number of elements, does not really make much sense here. Here, dimension is a better word, but very often we do call it order as well. Now, you have R cube conditions here. You also have R cube conditions here. This also has to be equal to minus CABC. It turns out that this condition and this condition are exactly the same condition. They're not different conditions. That this is equal to minus CABC and this is equal to minus CABC are the same conditions. Not so easy to see, but that will be an homework. Check that this equal to minus CABC does not give you a new bunch of equations from this. But let me just show you what this does give. I've just lost my equation right now, which is actually a bit of an unfortunate thing because I do need it for 2 more minutes or at least 5 more minutes. Okay, if I write the thing again, it's something like this. I'm using K now. Okay. I hope I've got this right. Okay, at which value, should the argument be here?
Sir, you wrote R again. The second time.
Oh, right. What would the argument be here? At what value of the parameters? What should I use, alpha or F?
Should use F.
I will use alpha. After all, we just showed that they are constants, right? They're the
So
same
it
for
doesn't
everywhere.
matter if you used F.
Doesn't matter what argument you use. Okay. So this is a bunch of equations which actually the etas and xi's have to obey. But let me just identify the CABCs for you using a very simple value for simple choice for alpha. সুখেন্দু আমি তোমাকে একটু পরে ফোন করছি So can anybody suggest a value of alpha? This can work for all values of alpha. Can anybody suggest a value of alpha for which this will be very simple? The left hand side. You have other complicated looking things, right? You have zetas, etas, derivatives, and so on. But can you suggest a value for alpha for which this expression will become considerably simpler?
If you have
The
alpha
origin.
0, then we get a delta function.
Yeah, if alpha is 0, then much of it will become very simple. This becomes delta, not delta function, delta symbol. This becomes delta KB, right? This becomes delta KC. So the J has to be replaced by A. What you end up with is eta A C comma B. And then let's put a minus sign here because I have a minus on the left hand side. Now, eta AB comma C, which is what is that? That's eta AB differentiated with respect to the Cth component of the argument. So that's del alpha C del beta B of f of beta semicolon alpha, right? At both alpha beta equal to 0. And the same thing with B and C interchanged. Clear? Eta AB, that's del F, okay, A. Del F A del beta B of beta semicolon alpha at beta equal to 0. But after that, you are going to differentiate with respect to its Cth alpha. And this is what you are going to get. Clear? So, CABC and finally, okay, is this clear before I move on to the final step? If there's no response, I'm assuming this is perfectly obvious. But remember, Fj of alpha beta, we just wrote down the expansion, right? At the beginning of this class. What was Fj of alpha beta?
Alpha j plus beta j.
Kth alpha beta. So plus higher order terms. Notice when you partially differentiate f with respect to alpha and beta, and then put alpha equal to beta equal to 0, the only term which survives is actually this. Two derivatives get rid of this, and then if you do two derivatives, these terms which have higher numbers of alphas and betas will actually still have alphas or betas left after differentiation. So when you put alpha beta equals 0, that will vanish. You will actually get CJKL the C's are directly related to these coefficients. By the way, AJKLs are coefficients of quadratic terms, and very often we are used to situations where in a Taylor series, coefficients of quadratic terms are symmetric, like say in the potential, when you expand this in small displacements. You have a symmetric matrix, and that might make it seem that this will vanish. But notice that AJKL multiplies alpha k beta L, not alpha k alpha L. So there is no reason why this has to be symmetric. Even it is not. The antisymmetric part is basically what the CJKLs are, the structure constants are. Okay, so we have gone quite a long way, but also the difficult part of Lie group theory is behind us now. What we did in the last class, and this class in particular, with this integrability condition, that is the difficult part. The rest will be much easier. Okay, I think I will call it a day. I've already overshot the time by some times. But that, remember, the lunch time is already mine anyway. Partly, a part of it is at least. Okay, hopefully see you on Wednesday, and hopefully see you face to face. Bye for today. who have to do several things.